Hi everyone, thank you so much for coming to this video. So today we're going to be going over the constant acceleration formulae. So please review the videos on the language of kinematics, displacement time and velocity time graphs, and also vectors, as we're going to be using that in this video. So the learning objective is to be able to understand, use and derive the formulae for constant acceleration, and also to be able to extend the constant acceleration formulae using vectors. So like always, there's going to be timestamps in the description of the video, so feel free to skip to any parts you want to. But let's get started. So if you are modelling a particle, a moving object which has constant acceleration, there are 5 different equations that we can use to model these. So these are also called the SUVAT equations because they use these 5 terms of SUVAT. So S in SUVAT, that represents your displacement in meters. Your U, that represents your initial velocity in meters per second. Your V, that represents your final velocity in meters per second. And your A, acceleration, represents your acceleration in meters per second squared. And your T represents your time taken in S. So that's why we're going to use all these variables to model constant acceleration. So that's why we can either call them SUVAT equations or just your constant acceleration formulae. And I've written these 5 here, and you don't need to remember them because you'll get them in your formula booklet, but you do need to know how to derive them. So we'll go through how to derive them shortly. So we have 5 constant acceleration formulae. The first one is V equals U plus AT. Then we also have S equals UT plus half AT squared, S equals a half times U plus VT, and V squared equals U squared plus 2AS, and S equals VT minus half AT squared. So now let's go on to how we can actually derive them. So we can derive this, so if we label these 1, 2, 3, 4, 5, so we can derive equation 1 and 2. 1 and 3 using our velocity time graph. So if you remember what a velocity time graph looks like, you have t on this side and velocity here. And then if we start from our initial velocity u, and then we have constant acceleration, so it's just going to be a straight line with positive gradient. And then where it ends, that's going to be our final velocity v, and the time it takes is t. So if you remember, the gradient of this line, that represents our acceleration. So if we first work out the gradient of our straight line, so that's just changing y over change in x. So our change in y, so if we draw a triangle like this, just do it in green. So let's say we have a triangle like this. This here, that represents v minus u. That's our change y, and our change in x, this line here, that's just t. So that means our gradient, that's just equal to v minus u over t. So then, because we know gradient is just acceleration, that just means a is just equal to v minus u over t. So then if we multiply both sides by t, we'd get at equals v minus u, and then if we arrange it, we would get v is just equal to u plus at, and that's our equation number 1. So that's how you derive v equals u plus at. You just use your velocity time graph, and then using the fact that your gradient is equal to your acceleration. So we can also use this graph to derive our equation 3. So if you remember, your displacement is just your area that's underneath your curve, so it'll be this whole red area, and that's in the shape of a trapezium. So if you remember the area of the trapezium, that's just your one side, which is just u, plus your other side v, all over 2, times your base, which is just t. So therefore we can call, and because this represents, the area under graph represents s, we can just say s is just equal to half times u plus v t, and that's our equation number 3. So you derive this equation using the fact that your area under your velocity time graph, that's just displacement. So now we can use these two equations to derive our other three equations just by using substitution. So if we start off by subbing in, so we have like two equations and we want to do substitution to work out our equations. So if we start off with by subbing v equals u plus at into our equation 3, then we could say that s is just equal to half times u plus at all times t. So that means that our s, that's just equal to a half times 2u plus at times t. Then if we multiply this out, we would get s is just equal to half times 2u, that's just u, times t, so it's ut, plus, then if we multiply this out, we get half at squared. And that's our equation 2. So now if we want to rearrange our equation 1 to find u, so we could say b minus at is equal to u. And so now we can just sub this into our equation 3. So we can just say that s is just equal to half times v minus at plus v times t. So if we simplify our brackets, we'd get half times 2v minus at all times t again. And then if we just simplify this, we'd get a half times 2v, that's just v times t, so vt minus a half at squared, and that's our equation 5. So the last equation we want to derive is equation 4, v squared equals u squared plus 2as. So the only variable that we haven't found, like through rearrangement, is t. So if we, from equation 1, we can say that v minus u over a, that's just t. So that's just rearranging equation 1, and then we can sub that into 3 again. So if we were to sub this into our equation 3 here, we'd get s is just equal to half times u plus v all over v minus u over a. So now if we were to simplify this, the first thing we can do is multiply both sides by 2. So if we were to sub this equation into equation 3, we could say s is equal to u plus v over 2 times v minus u over a. So the first thing we can do is just multiply, get rid of our denominator, so multiply both sides by 2a. So then we'll get 2as is just equal to u plus v times v minus u. So now if we just expand our brackets, we'd get uv minus u squared plus v squared minus uv. So then if we would get uas is just equal to minus u squared plus v squared, and then if we arrange it, we get v squared is equal to u squared plus 2as. So that's how you can derive all of our constant acceleration or SUVAT formulae using our velocity time graph, and then just using the two equations we got from that and just rearranging and substituting to get the rest of our equations. So there is another way we can derive that, and that's using calculus. So let's try that. So we can derive v equals u plus at and s equals ut plus half at squared, using the fact that if you differentiate displacement, you'll get velocity, as the velocity is just your rate of change of displacement. And then if you were to differentiate your velocity again, you would get your acceleration, as acceleration is just the rate of change of velocity. So therefore, if you do it your other way, if you were to integrate acceleration, you get velocity, and then if you were to integrate velocity, you would get our displacement. So let's try using all this information to derive these two equations. So we start off with v equals u plus at. So we know that because acceleration is just our dv over dt, is just differentiating our velocity, then you could say that our velocity is just the integral of a with respect to dt. So then if we were to integrate our velocity, then we could get, if we were to integrate acceleration, we get that is equal to AT plus a constant c. So we get v. In order to get our constant c, we can use our starting condition. So our initial velocity, so that means our v will equal u, and then our t at time, our t would be 0. So then you could just say that u is equal to 0 plus c, so that's just equal to c. So then if we plug this in, we would get v is equal to u plus at, which is our. Now if we move on to our second equation to derive, and we want to use the information that we just derived for this one. So if you remember velocity, that's just the differential of displacement. So now if we were to find displacement, that's just the integral of v with respect to dt. So now we just want to plug in our v that we found here. So that will be the integral of u plus at dt. So then if we were to integrate this, we get that is equal to ut plus 2a plus, if you raise t to the power of 2, so it'll be plus a half at squared plus c. So now we just want to do our starting condition, so when t equals 0, so then we'll just have f, and at starting condition, our s will also be equal to 0 because, well, there's no displacement from when you begin with, so then you would just have 0 is equal to c. So we can just plug this in to say s is just equal to ut plus half at squared, and that's our formula here. So that's everything you need to know about our constant acceleration formulae and our SUVAT equations. So let's try and apply these to some questions. So we have a question here. It says a car passes point A with speed of 20 kilometers per hour. The car accelerates at a constant rate, and 10 seconds later it passes point B with speed of 70 kilometers per hour. So the first thing is we want to find the acceleration in meters per second. So to do this, we just want to write out any information we can if we know any of our SUVATs. So we just write it like SUVAT. We just want to fill out all of these if we can. So it says it passes point A with speed of 20 kilometers. So that means our initial velocity is just going to be 20. And it says it accelerates constant rate, and 10 seconds later it passes point B, so our t will just be 10, and it says passes point B with speed of 70, so that means our final velocity, that's going to be 70. So now we want to find acceleration using one of these equations. So you want to see which formula has everything apart from s, because we don't know that. So we know that the only equation we can use is b equals u plus at. So if we use our equation b equals u plus at and just plug in everything we have, so we have our 70 is equal to 20 plus 10a, so that means 50 is equal to 10a, so that just means a is equal to 5 meters per second. So that's our answer to part A. So now if we move on to part B, we want to find the distance A to B. So we just want to find our A. So now we've got all our information, so we can just use any of our equations. But because we don't know if our part A is right, if you may not know that in exam, so try and use the formula that has everything apart from A. So we can do our equation 3. So we could just say S is equal to half times u plus vt, and just plug in all the values we have. So we have that equal to half times 20 plus 70 times 10, which is just equal to 5 times 90, which is just equal to 450 meters. So that's our answer to this question. So that's how you can use our constant acceleration formulae when in a question in the form like this. So you just want to write down all the values that we have for SUVAT and just find the value that you want to find, and then find the equation that you can use that has all the values that we have and that you want to find, and do the same for both parts. So let's try another exam style question. So we have another question here. Feel free to pause the video and try it out for yourself first. So one thing you do need to know for this is for gravity, your acceleration is always minus 9.8 meters per second. So that's just something you need to know whenever there's something gravity, so something being dropped from any point. So we have a stone is dropped from a point 120 meters from the ground. So the first part is we want to find the time it takes for the stone to reach the ground. So we just want to see that what we can. So now our displacement, because it's going from top to down, is going to be a negative value. So our displacement will be minus 120. Our u, that's just going to be 0, because from the point it starts, our stone's not going to have any velocity. We don't know our final velocity. We know our acceleration here is just minus 9.8 meters per second. So whenever you're going, something's dropping down, you have a negative acceleration. If it's going up, so from like, if you're throwing something up, you're going to have a positive acceleration. And then your time, that's what you want to figure out. So now that we've got these values, we don't know what our final velocity is. So we want to find an equation that has S, U, A, and T in, no B. So that is our equation number 2. So we could say, we can use S equals UT plus half AT squared. So we could just plug in our values. You'd have minus 120 equals 0 plus, so half minus 9.8 t squared. So we could just say minus 120 is equal to minus 4.9 t squared. So then t squared, that's just equal to 20 over 4.9. So then t is just the square root of that. That means our t is just 4.9 seconds. So that's our answer to part A. So now if we try part B, we want to find the speed at which the stone hits the ground. So we want to find our final velocity V. So we want to, because we don't know if our T is correct, we want to use our equation that has everything apart from T. So that's our equation 4. So you can say V squared is just equal to U squared plus 2AS. So V squared is equal to 0 plus 2 times minus 9.8 times minus 120. That means our V squared is equal to 2352. So that means our V is just 48 meters per second. So that's the answer to this question. So that's everything you need to know about our constant acceleration formulae and how you can apply this to some exam questions. So now let's go on to being able to extend this formulae for using vectors. So you could have your either of your SUVAT just written in the forms of vectors. So you just apply your constant acceleration formula normally, but you just have to do normal like addition or normal operations that you would do with vectors. So it's just using the same formulas, only that now your velocities or your displacements, they're just written in terms of vectors. So let's try this out with this question. Feel free to pause the video and try it out for yourself. So we have a particle P has position vector 3i plus j meters and velocity 2i minus 5j meters per second at t equals 0. Given that P accelerates at a rate of minus 2i plus j meters per second squared, find its position vector at t. So like we did before, we just want to write out all our SUVATs. So we have our displacement, so that's just going from 3i plus j to so we just want to write our SUVAT. We don't know our displacement. We know that our u, because we know that its velocity is 2i minus 5j at t equals 0, our u is just that. So we can write it in either column or component form. We can say it's 2 phi. Our velocity, we don't know our end velocity. We know our acceleration is minus 2i plus j, so we can just plug that in. Minus 2, 1, and we know our time will be 6. So we want to find the position vector at t equals 6. So that means we just want to know how far it's travelled. So we want to find our displacement. So we want to find which one we can use that doesn't have v in it. So we can use this equation too. So we could say S is just equal to ut plus half at squared. So now we just want to use rewrite this with our form, so we can have our t is 6 and our u is just 2 minus 5 plus a half times our time is 6, so times 36 times our acceleration is just minus 2 and 1. So now we can just do normal like vector addition and multiplication. So we'd have our s, If we multiply this out, that's just 12, so 6 times 2, then we want to do 6 times minus 5, so minus 30, plus a half times 36, which is just 18. So then we want to do 18 times minus 2, so that's just minus 36, and then 18 times 1, which is just 18. Now we just want to add this normally, so we want to do 12 minus 36, which is just minus 24, and then if we do minus 30 plus 18, so that would just be equal to minus 12. So that's the displacement that happens. So now, because we want to find our position vector at time t equals 6, so it's going from position vector 3i plus j to minus 24 and minus 12. So we want to find the difference between that. So all we want to do is our position vector will just be our initial position, which is just 3, 1, plus how much is travelled next. So it's travelled minus 24 and then minus 12. So if we plug that in, that would just be equal to minus 21 and minus 11. So that's our new position vector at time 6. So that's the answer. So if you have vectors, everything written in form of vectors, you just want to write out your vectors normally. You just want to do what we normally do for constant acceleration formulas, just write out our SUVATs and see which equation will be most suited, knowing the information we have. And you just want to do normal vector addition and normal vector multiplication. And just be careful for the last step. The distance, our s here, that's just displacement, it's not the distance. So to find out our last position vector, you want to go from your original position vector plus our displacement to get our final position vector. So that's everything. Thank you so much, everyone. Hope you found that useful and you now understand how to derive and use the formulae for constant acceleration, which are written here. And you can also use these with vectors. So make sure you do some practice questions just to make sure you fully understood everything that we've covered.